Okay, we're going to quickly review some things about momentum to understand it with impulse. Last week you were assigned some things dealing with both momentum and impulse, and hopefully this explanation mathematically will make things a little bit more clear. So the last time I saw you guys, we went over the simple fact that momentum, P equals mv, mass times velocity, which the units were kilogram meters per second. Now we're going to define another thing that is closely related to that called impulse. Impulse is uppercase J, and it equals force multiplied by time. It has the same units of momentum, or another unit that does mean the same thing, if you derive it correctly, is Newton seconds. So either one's okay. Now, really, both impulse and momentum totally by themselves don't do a whole lot for us. What's really important when we put them together in what's called the impulse momentum theorem. Written as condensed as possible, it says impulse J equals change in an object's momentum, delta P. Breaking it down to a more useful form is F times T equals mvf minus mvi. Let me get rid of a few things here before we go on. Okay, so what does this all mean? And I'm going to give you an example, a poorly drawn example of two people jumping and hitting the ground at the same level. All right. So let's say we have two people jump from a fairly high height and they land and hit the ground. Person A on this side hits the ground and doesn't bend their knees. Person B on this side hits the ground and does bend their knees upon impact. So what would happen, hopefully to most of us, is that we would bend our knees. That's something we naturally do without thinking about. So, but if you wouldn't, the stopping time would be very different. So the person who, let me erase one more thing here. The person who does not bend their legs or bend their knees on the left side would have a much smaller stopping time. We'll just say T is low as compared to the person who hits and does bend their knees. And what would happen with the force, we'll see in a minute in the formula, is if you have a smaller stopping time that causes a greater force upon impact. If you have a larger stopping time, that would create a smaller stopping force. So by nature, we know that it's going to hurt if we don't bend our knees when we hit the ground. And it won't hurt as much because that higher stopping time will cause a lower force. If you leave your legs stiff and hit the ground, that smaller stopping time will result in a larger force. And it all happens over here in the impulse momentum theorem. We could see if we solve this for F that T would get divided to the other side, making them inverses of one another. It would cross out there, and you can see F up top and T on the bottom. And anytime we have an inverse mathematical relationship, that means as one thing gets higher, the other thing gets lower, or vice versa. Another example would be catching an object, like catching a football, let's say. If you would hold your arms out real stiff and rigid and the ball hits your hand, you're likely going to drop it and probably stub your fingers, because you would be like the person who doesn't bend their knees. You would have a low stopping time for the ball, which creates a high force and a higher likelihood that it's going to bounce off you. But if you give your hands more like the guy who bends his knees, if you give and have soft hands and bend your elbows and bring the ball in, you'll create a higher stopping time, resulting in a lower force, resulting in the fact that it'll be easier to catch the ball. Last week, I assigned you guys a video to watch about car crashes, and here's a problem based off something like that. So let's put some numbers into this stuff. We have a 1,000 kilogram truck moving at 20 meters per second, and it's going to come to rest by braking in 4 seconds for scenario A. And in the second set, it's going to crash into a wall and stop almost immediately in 0.1 seconds. In both cases, we want to find the force required to stop the truck. So let's start listing some givens and do the braking portion right now. And we see we have a mass equal to 1,000 kilograms, an initial velocity of 20 meters per second. And in both cases, we're going to have a final velocity of 0. We're going to come to a stop. But the big difference is the time. In typical braking, it'll take a few seconds to stop. So in this case, it's going to take 4 seconds in part A for the truck to stop. So if we use the impulse momentum theorem and solve for F by dividing T over, we could see if we plug in all those givens above, that there'll be a 5,000 Newton stopping force on this truck in a normal braking situation. And yeah, that's a kind of large force, but it is, even in regular normal braking, is going to take quite a bit of force to stop a 1,000 kilogram truck. But if that truck would be in an accident and hit something stationary, let's say a wall like in this problem, that time is going to go down greatly to 0.1 seconds. Everything else will be the same. Still the 1,000 kilogram truck, still coming to rest, and still 20 meters per second initial velocity. This time we're going to divide it by 0.1 instead of 4 and get out 200,000 newtons. Now that's a huge difference right there between those two. And this shows the same exact idea as somebody jumping and bending their knees as opposed to not bending their knees. So we see that in part A, the time was much higher, therefore the stopping force was lower. In part B, the time was much, much lower and created a really high stopping force. You wouldn't want to be inside that truck if it took 200,000 newtons to stop it. And finally, just a quick derivation of where the impulse momentum theorem comes from. It's simply by taking an old thing, Newton's second law, which we've done before, and a kinematic equation, the one that does not have D, and doing a little substitution. If I solve this kinematic equation for A, sub it in here, and distribute the M down in the next step, we can make this look exactly like the impulse momentum theorem. So it didn't come out of nowhere. That's the origin of it, some old stuff we already learned. I hope this helps you guys better understand some of this stuff you were studying last week. As always, you can always feel free to email me or get me on Remind for any further explanations, for any assignments, if you have questions.